Uh, Good morning, everyone. Can you guys hear me?
Yes.
Okay. Good morning. Once again, I actually want to welcome you to my lecture today. Today, July 2nd, actually going to be discussing a new topic. This topic is actually based on Otelin T squared. I'm actually going. This topic, what we want to do here is more or less like application, okay? But the focus is actually going to be on WNBA regular season, okay? WNBA regular season, home point spread, and over and under differential 2010 to 2018, okay? So uh, the application will actually be based on that. So, like I said, let me welcome you to the topic today. We call it approximately bivariate normal data, an inference based on Otelin T square. Okay, so we actually going to be working on two variable, and that is the word bivariate. Okay, and these two variables have been assumed to follow normal distribution, and we actually want to we want to make inference, we want to make statistical inference on this bivariate data using Otelin T square that you have learned in class. Okay, and that's exactly what we want to do today. Okay, so I hope you're going to enjoy today's lecture. Let me tell you, yesterday I was a little bit sick, and I was not that and that was why I was not at. Maybe I didn't attend to your mail. But for those who have sent a mail to me, who are expecting response, okay, they're actually gonna get my response today. Was yesterday I had emergency, but I think I'm good now. Okay, so like I said, I'm gonna be walking you through bivariate normal data and inference based on Otelin T squared. And you know what? After, if we're able to finish this on time, then I'm actually going to start an entirely new topic. Okay, so if you look at what I put right here, approximately, okay, you know, most of the data set that we have that do follow normal distribution, they don't really follow normal distribution exactly, okay, because we are in an approximate world. Okay, we are in an approximate world. Okay, and that is the reason, even if data set is actually going to be normally distributed, it's actually going to be approximately normally distributed. Okay, so like I said, what we want to do here, we want to collect to, pretend as if you are working on two variables. It could be from sociology, it could be from psychology, it could be you could be doing a medical research, or you could be doing anything that has to do with sports. Okay, and in such a way that these two variables are correlated. Okay, they have to be correlated. Okay, before you can actually have a joint distribution for them. You remember when we were dealing with bivariate normal distribution? Under bivariate normal distribution, we have an assumption that correlation has to be greater, must not be equal to zero. Okay, so which means the two variables under contention are correlated. Okay, and when they are correlated, they can actually be distributed normally. Okay, they can have a joint normal distribution because they are correlated. Okay, if they are not correlated, automatically, even if they're going to follow normal distribution, and that will be marginal. Okay, But what we want to assume today is that, okay, the two of them are jointly related. They are jointly correlated. And as a result of that, the bivariate density can actually be used to simultaneously capture them. Okay? So, like I said, the two major variables that we want to talk about, okay, using the WNBA regular season, okay, are the home point spread and over or under differentials. So these are the two major variables that we're actually going to be working on today. Okay. Now, in this slide, I actually want to provide a background, so that you're actually going to have the knowledge of the data set. Okay. Like I said, the 1,833 WNBA regular season games are being considered, okay, with home team points spread and over other total lines during 2010 to 2018 regular seasons. Okay, it's just like the number of games that was played in 8 years between 2010 and 2018 in WNBA. Okay, and then you know what? You remember the other time I was teaching something on linear combination? The two variables that we actually want to consider, they are also function of some other set of variables. I'm going to say that again. The two variables that we actually want to consider, when I say the two variables, I'm referring to the home spread deviation and over and order deviation. Okay? I'm referring to home spread deviation and the over and order deviation. But you know what? The home spread deviation is also a linear combination of another set of variables, okay, that we actually need to figure out, okay? And the same thing also applicable to over and order deviation, okay? So right here, the first variable, the D1, okay, which is the home spread deviation, is a function of x1, x3, and x4, okay? And what is my x1? What is my x3? What is my x4? Now my x1 is right here, the home point spread line, okay? The home spread point line, okay? And this is the description for that, okay? So the over and under total point line is x2, which is the expected total point by both teams in the game, okay? Before two teams engage themselves, there's going to be what I call expectation about what is going to be their total point, okay? From some football or specialists or some football analysts, okay, can actually predict the total points in the game before a particular game is played. Okay, so home team score is x3. Okay, home team score is x3, and away team score is x4. Away team score is x4. So if I want to get the home spread deviation, of course, this is what I'm going to use. Why is it that x4 is minus? Of course, if I'm talking about home, okay, if a away team score your team in your home, okay, for instance, let's assume that we are working, let's say we are referring to Timberwolves. Has any one of you heard about a basketball team called Timberwolves in Minnesota?
Yes.
Okay, thanks for that. Okay, so let's assume that Chicago Bull visited Twin City to engage Timberwolves, and then the Chicago Bull or whatever team, maybe Golden State Warrior or whatever team that visits Timberwolves, if they score points uh, here against Timberwolves, that would be negative to Timberwolves. And that is the reason why you have X4 to be negative right here. Okay? That is a away team score. A away team score to the home spread is actually going to be a negative. Okay? So what is going to be positive is going to be X1 and X3. And what is my X1? The X1 is going to talk about the home point spread line. Okay? And the X3 is actually going to be home team score. Okay, so the home point spread line and the home team score, they're actually going to be a positive, of course, because we're dealing with the home spread deviation. Okay, so when you now move to the second variable, which is D2, I'm still going to use a combination of X1, X2, X3, and X4, but only that what I'm using here is different from what I'm using here, because now I'm talking about over and order deviation. Okay, I'm still going to have S3, but this time around I'm going to have X4, because for the away team, okay, then I'm going to have a negative X2. The X2 here is actually going to be over under total line, which is the expected total point by both team in a game, and that should be a negative. Okay, so all what I'm trying to showcase right here is just that, okay, you know what, we need two major variable, which is D1 and D2, but these two major variables are actually dependent, they are linear combination of other set of variables. Okay, so what we're actually going to be using is going to be D1, D2. So we're actually going to pretend as if we have the X1, X2, X3, X4. Okay, so over 1,833 games. Okay, so from there, from each of that, we're able to compute D1, D2. Okay, so it means in my column, D1, okay, I'm going to have two collected over what is going to be the experimental unit. The number of experimental units here is going to be 1,833 games. Okay, and that's exactly, we're going to be working on the D1 and D2 right now. Okay, so the assumption is that the D1 and D2 right here are correlated. Okay, they are correlated, and at the same time they are jointly normally distributed, and that is a bivariate that I talk about, bivariate normal density that we talk about. Okay, uh, coming to the population data now, like I said, we are actually working on 1,833 games played in the WNBA between 2010 and 2018. Okay, I'm going to take you back. You can see the year 2010 to 2018 regular season. Okay, now we've defined our D1, we define our D2, and of course that is going to be a vector of two variables. Okay, vectors of two variables where each of the variable, the number of the data set under that is going to go from 1 to big N, and you know what the big N actually going to be, the number of games that we considered over the years under investigation. Okay, now of course, this is just trying to tell you, okay, I want to find the mean. I want to get the mean vector of these two variables. Okay, so using 1,833 for the first variable, okay, this is what we got as the mean. Okay, the mean of the first one, and this is going to be the mean of the second one. I believe if I give you some set of data set about this, I know you can actually figure that out. Okay, that's going to be so easy. Okay, now you know that when you have a vector of mean, of course you also need to set up what I call your variance covariance matrix. Okay, so this is your variance covariance matrix. It's going to be 2 by 2. Okay, it's actually going to be 2 by 2 because the number of variables is 2. If I have 3 variables, it's actually going to be 3 by 3. If I add 4 variables, it's actually going to be 4 by 4. Okay, so because I got 2 variables right here, this is actually going to be 2 by 2. So what am I trying to say? The first variable here is the variance of the home spread deviation, and this is the variance of the over under deviation, and what I have right here are the covariances. Of course, the covariance, the value here is also going to be equal to here, right? Okay, based on what you have here, you can actually find your correlation value. Okay, I've taught you this before. Okay, so that this will actually tell you, um, you know, it will tell you the strength of the relationship and the direction of the relationship between the home spread deviation and over another deviation that we are actually investigating. Okay, like I said, the row here actually confirm that there's a correlation between them. Okay, now, so and then approximately, we have carried out any of the multivariate normality tests that I taught you before, the energy test, and so on like that. Maybe that has been done, and we now realize that the data set D, when I say data set D, I'm referring to the vector of 2 variables. So are jointly normally distributed. The N2, the 2 that you see here, is trying to tell you we're talking about bivariate. Okay, the 2 that I put here, we're trying to say that, oh, we got the 2 variables inside this very D here, normally distributed with a mean vector data. Okay, this is the mean vector right here, which is representing this. Okay, can you see that now? And with a variance covariance, this guy here, so which is this guy here, which is equal to this. Okay, so this is the normal distribution. This is the distribution of these two of the bivariates of variable the under investigation. Okay, and you know what? You may actually want to look at investigate the normality of the data set right here. You know, using the virtual means. Okay, so what I have right here now is the normal QQ plot. Okay, the normal QQ plot of the 2 variables under investigation. And as you can see, the first one right here, this is a sign of a normal distribution. Okay, this is trying to tell you that the home spread, home spread deviation is normally distributed. And take a look at this guy here. Okay, take a look at this guy here. Is also normally distributed, only that is approximately normally distributed because we got some kind of inch right here. Okay, and that was why we mentioned, okay, they are more or less approximately normally distributed. Okay, I think you get that now. So is there anyone who actually want to ask question about uh, what we just did right now before I move to the next slide? Is there anyone? Can you guys hear me?
Yes.
Okay,
Yes.
okay. Thanks for that. Okay, so I'm gonna go to the next slide right now. Uh, if you look at this slide, you remember yesterday when I was walking you through simultaneous confidence interval, that the simultaneous confidence interval is called ellipsoid, where we use a formula and we get 2 sets of uh, intervals, right? And the 2 sets of intervals can actually be used to construct an ellipse. Okay, so what I'm showing you right here is just that, okay, I've done a 95% confidence interval. Okay, if you follow what we did yesterday, you're actually going to have what I have here. Okay, so this is the center. Okay, this is the center of of the data. The center of the data here is just talking about this guy here. Can you see now? So that's going to be the center. Okay, that's going to be the center. Okay, so, and as you can see, this is 0. Okay, these are negative. Okay, so this is starting from negative to positive, and this is from negative as well, because when you look at what we got here, part of what we got here, you can see a minus, right? And that was why it's like that. So what I'm trying to say, a 95% simultaneous confidence interval have been done, and we actually come out with this. Okay, that's exactly what I'm showing you. And don't forget yesterday that the point here, okay, is the upper limit, and this is the lower limit of one of the intervals, and this is the lower and the upper limit of the other interval, and that actually form an ellipse. Okay, I think I showed you this yesterday. Okay, so the next thing that I want to talk about now, I want to talk about sampling distribution of mean vector and variance covariance matrix. Now, why do I need a sampling distribution of mean vector? Let me remind you that in a univariate uh, analysis, where the interest is just on one variable, okay? When the interest is on one variable, if I go into a population and I take a sample size of 10 and I find the mean, okay? If I go again into that same population and I take a sample size of 10, of course, there is possibility, since I'm sampling at random, the what I selected in the first time I visited that population will actually going to be different from what I'm going to select when I go into the population second time. Okay, so which means the value, if I compute the mean based on what I selected in the second time, the mean will be different from what I selected in the first time. Okay, and that is the reason why we actually need to have a sampling distribution of the mean, because the mean, we know we are actually going to have different kind of means, because the number, if you go into population several times, you're going to have different kind of means. Okay, therefore you need to consider the probability distribution of the means, and that we call sampling distribution of the means. Okay, we can also do that in a situation where we are working with more than one variable. Okay, and that's exactly what I'm talking about here. How do we do a sampling distribution of mean vector and the variance covariance matrix? Okay, now we got D1 up to dp. Now D1 up to dp, we want to assume that the number of variables, we got p number of variables, right? And this is a vector mean. Okay, and of course, this is the variance covariance. Of course, it's going to be p by p, because the number of variables here, you know, is p. Okay, and you know what? This guy here is the same thing as the expression that we have right here. Okay, now take a look at this. When I go into the population, if I want to find the mean, okay, I'm going to find the mean of the variable one at a time. Can you see what I have? Okay, this is a uh, more or less like the standard deviation vector. Okay, now when I do that, you know, every time I go into the population, for each of the vector, if I take sample size, I'm actually going to have, you know, a different kind of means. Because of that, I actually need to find the average of means. When I have several means, we have means, is a random variable that we can look at the mean of means. So here, what I'm doing right here, expected value of mean, or expected value of mean, it means I got several means, and I'm actually want to figure out the mean of the several means. Then when I do the same thing to variance, okay, when I go into the population on each variable, okay, when I take a sample size of 10 or whatever, I compute the variance. When I go into that population again, I take a sample size of 10, I compute the variance. The variance I'm going to compute based on one variable, using in the first time I visited the population will be different from the variance I'm going to compute when I go into that population again. Therefore, variance is also going to be a random variable. And if a variance is if that is what happened, then it means, how do I figure out the mean of that? Okay, so what I'm trying to say right here is that, okay, I got several means, okay, and I want to find the mean of the mean. Okay, and this guy here is trying to say, okay, how can I find the variance of the mean? Okay, the variance of the means. You remember in the univariate setting, okay, the variance of x is sigma squared, right? But the variance of x bar is sigma squared over n. I'm going to say that again. The variance of x, of a random variable x, is sigma squared. But the variance of x bar, where x bar is the mean, but because we have several of them, the variance of x bar is going to be sigma squared divided by n. Okay, and that's exactly what we're trying to say right here, that, okay, you know what, in a situation where I got a vector of mean, I mean, when I got a vector of mean, several mean that changes, the variance of that will actually going to be 1 over n variance covariance. Okay, it means the variance covariance that I've obtained before, I needed to divide them by n, because we did the same thing in univariate setting. Okay, in univariate setting, we know the variance of x is a sigma squared, but the variance of x bar, then I need to divide my sigma squared by n. I'm also good. That's exactly what we're trying to do right here. Okay, that, okay, because the variance covariance, what I have there, the sigma d that I have here, is a variance covariance that has to do with d. But when I want to look at the variance covariance that has to do with d bar, then I have to divide that by n, and that is why I'm trying to divide this by n right here. Okay, and that's exactly what we're trying to do. Okay, so and you know what? Uh, these are just notation. That's theoretical notation. The expected value of xd has to be equal to that. That is just a notation. But you know what? We want to have a conclusion right here. If I have a d1 up to dn, you know, that are variables. Okay, what am I trying to say right here? What I'm trying to say right here is that uh, in a multivariate situation where I have so many variables, and you know what, to decide on the mean. Okay, let me give you this as an example. Let's say I have three variables. Okay, let's say I got three variables. Maybe I get height, weight, and blood pressure. I'm going to say that again: height, weight, and blood pressure. Now, these are my three variables. Okay, they are correlated. Okay, maybe pairwise correlated. Okay, now taking a look at this, if I go into a population and I take a sample size to determine the mean of the first variable, I did not visit that population only one time. I visited that population maybe more than one time. Okay, if I go into the population 5 times, it means I'm going to have 5 values for mean. Okay, I'm going to have 5 values for the mean of height. Okay, I'm going to have 5 values for the mean of weight. Okay, I'm going to have 5 values for the mean of blood pressure. Okay, because I have more than one sample. I go into population several times. Okay, that's exactly what I'm trying to talk about. So in that situation, I will need to be talking about, since I have 5 values for the means of the height, I need to find the mean of the mean. I need to find the mean of the means. I need to find the variance of the means, because the means is a random variable here because it varies. Okay, and that's applicable to this. That's also applicable to the second variable, and so on like that. So if I have so many variables, it means if I were to figure out about the mean and the variance measure of each of them, I have to visit the population more than one time. When I'm doing that, I'm actually doing what we call a sampling distribution. Okay, so what I'm trying to tell you right here is this. Okay, the D1 of Dn, you know, is IID. Okay, normally identically, and independently normally distributed. Okay, it's going to have this as the mean, and having this as the variance covariance. Then, we know this one right from time. Okay, here we have not done any, so we have not gone into the population more than once. But when we go into the population more than once, okay, in such a way that we want to find the mean of the means, then this is what we're going to have. The distribution will be different from this. Like what I have here is the distribution of D, but what I have here is the distribution of D bar. There is a difference between the distribution of D bar and the distribution of D. When you're talking about D bar, we are actually talking about sampling distribution of the means. Okay, it means I visited the population more than once. Okay, and when I visit a population more than one, the first time I go into that population, I select a sample size of 10, I find the mean. When I go into the population again, I select a sample size of 10 randomly, I find the mean. The mean I'm going to get in the first time will be different from the mean I'm going to get in the second time. If I continue to go into that population, I'm actually going to have several means. If I go 10 times, I'm going to have 10 different values of means. Then the 10 different values of means are random variables now. Okay, therefore, because it's a random variable, then I'm actually going to have a D bar, also follow normal distribution with, this is going to be the mean, and this is going to be variance covariance. Now let us compare what I have here with what I have here. They're still going to have the same mean. Look at that, the same mean, but they're going to have a different variance covariance, because right here, this is a variance covariance, but right here, the variance covariance here, you have to divide by n. So this is more or less like a standard error. Okay, this is more or less like a standard error. Okay, this is more or less. But you know what? It's going to be a standard error when I find the square root. Okay, you know that. When I have the variance of x bar, the variance of x bar equals sigma squared divided by n, right? If I want to find a standard error, I'm going to find the square root of that. Okay, so right now I'm still going to call it the variance of d bar. Okay, now remember the other time I told you n minus 1 multiplied by the variance covariance, we actually follow a Wishart distribution. I think I told you before. We actually follow a Wishart distribution. And you know what? If I'm talking about univariate, okay, if I have n minus 1 multiplied by variance, that will be distributed chi-square. You know that? I told you. But when I have n minus 1, and this is variance covariance, then it's actually going to be distributed Wishart, because the Wishart is more or less like a generalization of a chi-square in multidimensional. Okay? Now, if that is what you have, okay? Now, let us now look at the Ottolenghi square. Now, the first thing is, why do I need to talk about Ottolenghi squared? Because we may actually want to test an hypothesis about the about variables. Okay, like if you look at the WNBA that I'm talking about, we may actually want to test an hypothesis about the two variables right here. Okay, whether their means are equal or not. Okay, we can actually construct a confidence interval. Of course, this is a simultaneous confidence interval that I've constructed right here, the one I call the ellipsoid. But you know what? Based on what we did yesterday, we got 4 ways to obtain simultaneous confidence interval in multivariate setting. Okay, this is just one of them. Okay, I remember yesterday I gave you one at a time confidence interval. We also talk about T-square confidence interval, and we talk about Bufferoni confidence interval in the multivariate analysis. Okay, this is just one of them. Okay, now we want to, some of you will be wondering, why do we have to go through the sampling distribution? Okay, uh, to be able to figure out Ottolenghi square. Let me tell you something. Statistical inference is actually based on sampling distribution. I'm going to say that again. Statistical inference. When I talk about statistical inference, yeah, it's either I'm talking about estimation or talking about hypothesis testing. Those are, you know, are based on the foundation of sampling distribution. Without sampling distribution, we may not be able to do that. Okay. Now, take a look at this. I got a random sample of size n for D1 up to Dn. D1 up to Dn are variables. Okay. But you know what? From each of these, you visited the population several times. Okay. Of course, this is a way to find your mean. Okay. This is your, you know, uh, the way to find the variance or the covariance. Okay. Now I said the D1 of the Dn actually follow multivariate normal distribution with this, but for sampling distribution, where you have in a situation where you have more than one value for mean for one variable, okay, and you can only have more than one value for mean for one variable where you have visited the population more than one time. Okay, in that situation, of course, we're going to have a different distribution for D bar. Of course, I show you that the distribution for D bar is right here. Okay, now in this, let me tell you something. Our D here from D1 to Dn represent deviations. We're still talking about WNBA. Okay, look at D1, D2, they represent deviations. Only that here we're using two variables. There are more than that. Okay, we are only using two variables. So here we are considering a situation where we're going to have more than two variables. Okay, in the regular MBA season, we only consider D1 and D2. They are more than that. That's what I'm trying to tell you right now. Okay, now if I find the average of the deviation, okay, and we expect that if this is the sample mean, okay, if this is the sample mean, okay, this guy here is a population mean. Look at that, the population mean of that is what is stated right here. The population mean is a true mean. Okay, now we may also want to get what is the distribution of the difference between the sample mean vector and the population mean vector. Of course, that's exactly what we want to figure out using Untitled squared. Because when you want to test an hypothesis about whether the values of a vector of mean can be hypothesized to be something, of course, what you're going to see us doing at the end of the day in the formula of the Untitled square we're actually going to be using is going to be talking about deviation. Deviation of what? It's going to be the difference between the sample mean vector and the population mean vector. Okay, the difference between the sample mean vector and the population mean vector. Okay, and that is exactly what you're going to have. That is what you're actually going to have in in Untitled squared. Okay, so what I'm giving you right now is just to be able to, show you the theoretical development of the reason why, what was used in the process of us having an Untitled square formula that can actually be used to test an hypothesis. Now, here now you know there is a difference between the sample mean vector and what? And the population mean vector. Okay, and that follows a normal distribution with mean zero, because why mean zero? We expect the difference between the sample mean vector and the population mean vector to be zero. That is our expectation. That doesn't mean that is going to happen. And that depends on what we're actually going to come out with at the end of the day in the experiment. Okay, now, and this guy here is the variance, is the variance of this difference. Okay, and don't forget that I told you that n minus 1 as they actually follow Wishart distribution. Okay, and you know what? This is just trying to tell you the theoretical development of a t-squared. But you know what? If we observe Random sample. Now, if we, because this happens to do with the population, and that's why I'm using D1, uppercase D1 up to uppercase DN. Let us assume that we now have a we now observe a random sample of D1 up to DN, where each of the D1, D2 up to DN are random, they are deviations, okay? They are, they are taken from the NBA. Like I said, in the data set that we use right now, we only consider D1 and D2, but it could be more than that. Okay, so, and this is the mean of each of that. And this is the, way to figure out the variance or the covariance. Let us now assume that we want to test an hypothesis about a particular, about the hypothesized, the value of a vector mean. Maybe we are saying is equal to a data naught, or it is not equal to data naught. Of course, we're actually going to use, you remember this is the same formula we use for, this is Ottolenghi square formula. Okay, this is Ottolenghi square formula, only that we wrote that to suit the random variable D that we're talking about. So this is an Ottolenghi square formula. I think you can see that now. Okay, this is the critical value of the Ottolenghi square, because after computing this guy here, I'm actually going to compare this with this. Okay, if t squared, if the test statistic value of the t squared is greater than the critical value, of course, we're actually going to reject the non-hypothesis. We did that yesterday. I walked you through that yesterday. And this is what you are going to use to figure out the p-value. Okay, and this is the simultaneous. I walk you through this as well yesterday. This is the 1 minus alpha 100% simultaneous confidence interval. Okay, for that. Okay, so just to be able to tell you, so what is the essence of showing you this is just to be able to tell you what led to the formula of a t squared is just as a result of the baseline integration of sampling distribution. Okay, so, and that was why we have that. Okay, now let us now have let's sampling from the population right now. Now we want to sampling from the population. The number of random sample is 100,000 and the sample size is 50. Now what am I talking about? I'm going to go into population 100,000 times, and in each of the 100,000 times, I'm actually going to be taking 50. I'm going to be taking my sample size is going to be 50. Okay, I'm 100,000 here means is the number of times that I choose 50 from a population, from the target population. Okay, so what I'm doing right here now is like sampling with, trying to, this is like a replication. Okay, going to the population, so number of time. Okay, and for each sample, okay, for each sample, don't forget that we're actually going to have how many samples are we going to have? 100,000 of them. So for each sample, okay, we're going to find the mean vector and the variance covariance matrix. So it means the number of mean vector that we're actually going to have will be 100,000. The number of variance covariance matrix that we're going to have will also be 100,000, because if I go into population once, okay, if I go into population once and I take a sample size of 50, of course, I will, that will give me one mean vector and one variance covariance. But when I go into the population 100,000 times, I'm actually going to have 100,000 number of mean vectors. And I'm also going to have 100,000 number of variance covariance matrix. Can you guys hear me?
Yes.
Okay. Is there anyone who need clarification, in what I just said right now about going into the population 100,000 times, and in each of these times selecting 50, and the 50 we are selecting, it's over several number of variables. Is there anyone who have a trouble time, catching that? Is there anyone? Okay. Silence implies that you guys are good. Now, like I said, for each sample, we actually want to test. We want to obtain a 95% confidence interval. We want to compare univariate distribution of mean difference with a theoretical distribution. We actually want to plot the mean differences with a superimposed bivariate normal episode. We want to graph the histogram of the scale t-square statistic with a superimposed F distribution. We want to compare mean and variance of sample variances and covariances with the theoretical values. We're also going to graph histogram of scale correlation coefficient with T density. Okay, we want to actually do that. Okay, we are actually investigating. Okay, now take a look at what I have here. We want to we have gone in, when we go into population 100,000 times. Okay, the sample size is 50, and at each time we are focusing on two variables. Okay, we are focusing on two variables. Now let me tell you this. Where is the population? Which population are we visiting? We are still visiting that WNBA. Look at this. The number of data sets remain 1,833. But you know what? I can come into this population more than 1 billion times to select a sample size of data. Okay? I can come into this population more than 1 billion times. Okay? To select some, because I'm going to be selecting sample randomly. So we're still using this data set right here. Okay? So now to be able to tell you that, okay, only that at a time, the sample size was 50. So let me tell you this. It means we're actually going to have in every time we go into that population, we're actually going to have mean vector. Okay, we're actually going to have variance covariance. Therefore, since I've gone into the population 100,000 times, I'm actually going to have 100,000 number of mean vectors. And I'm also going to have 100,000 number of variance covariance. Okay? Do you get that one now? Now, take a look at what I have right here. And you take a look at what I have right here. Okay? Now, you're actually going to see what I have right here. This is like showcasing, one of the time that I actually go into the population. Okay? Now, this is a variance covariance, and what I have here is I'm dividing each of these by n. Okay, why am I divided by n? Because I told you in the sampling distribution, I'm going to take you back now to see what I'm talking about. Okay, look at it right here. Okay, when you divide by n, it means I'm talking about the variance of d bar. When I say variance of d bar, it means that will actually give me the variance, the covariance. It's going to give me the variance covariance of the several mean vector. Okay, so this is assumed right now. What I have right here is actually assuming to be that. Okay, now under the empirical results, now this is what we expect. Okay, when I put a population right here, everything from here, this is just our expectation. Okay, this is expectation. Okay, now let me tell you, take a look at this. Minus is 0.1525. I'm going to show you something right now. Now, this is what we got before, right? Take a look at this guy here. Okay, I think you can see that now. I'm going to take you, I want you to see something. What I have here and what I have here is what I showed you before. Okay, now from a theoretical thinking, then our thinking is going to be, okay, if I want to get the variance of d bar, I should just divide each of these by n, which is this guy here. which is the variance covariance of the data. So this is our expectation. Okay, but when we go into the population, we have, looking at this, we have not visited population 100,000 times to be able to have what I have here. What I have here is just visiting that population one time. Okay, but when we go into empirical results, okay, we have visited the population 100,000 times. Okay, when we visited the population 100,000 times, we're actually going to have 100,000 values of mean of each variable. Okay, now what I have right here, it means I find the mean of the means. How many means do I have? 100,000 means. Okay, this is the mean of the means. For first variable, this is the mean of the means for second variable. As you can see, I'm dividing by 100,000. It means that after going, because we are under empirical result right now, we have visited the population 100,000 times, and we're going to get 100,000 values of means, and we find the average of that. That gives us this for the first variable, and that gives us this for the second variable. So what I have right here now become D bar bar. Why is it D bar bar? This is the mean of the means. Okay, what I have right here, I have so many. I have 100,000 variance covariance, and what I have right here, I added 100,000 variance covariance together and divide by 100,000 to be able to have this. So which means what I've applied here is the addition in matrix. It means I have 2 by 2 matrix in 100,000 times. And I added all of that together and I divide by 100,000, and then I have this. And this is now the mean of the variance covariance. Okay, can you see that now? This is the mean of the variance covariance. Then at the same time, I can find the variance of the D bar. This is the formula to find the variance of the D bar, and this is exactly what I have. Now we can now use utility squared, to test an hypothesis. Okay, we can use utility squared to test an hypothesis. So based on what I have here right now, okay, look at that. Our utility square formula is now going to change to something like this, where what I'm going to be using right now will be different from what I used before. Okay, now take a look at what I have right here. You can see what we call a D bar here. You can see you can see them. Okay, so we're actually going to be using what I have right here. Okay, and at the end of the day, by the time we compute that, of course, with the probability, the p-value associated with that is a 0.04621, and which means we are actually going to fail to reject the non-hypothesis under at 0.05, at 0.01, but we're going to reject that at a 0.05 because what I have here is 0.04 is less than a 0.05. Okay, we are rejecting at a 0.05 level of significance, and this is going to be the simultaneous confidence interval, the formula that we're actually going to use, and this is the Bufferoni correct formula to figure that out, where we can consider the convergence rate of that. So what I'm showcasing right here is applying utility squared when sampling distribution is involved. Okay, and I show you, but I'm actually going to, explain this more on Friday. Okay, I'm going to explain that more on Friday. Now, this is the histogram of mean ohm spread. Okay, why do I need a histogram? To be able to see the shape, whether it follows normal distribution or not. Okay, the two variables that I use. Okay, this is the histogram of the first one, and this is the histogram of the second one. And with the histogram, we'll be able to know the center. Okay, the center is going to be the mean. Okay, and this is the 95% probability episode. that I talk about. Okay, and this is the histogram of the scale t squared. We are able to get this using a sampling distribution. Now, let me tell you something. Somebody may ask, why do we need a sampling distribution? We need a sampling distribution. Maybe if the distribution of the variable are not normal in the first place, with the sampling distribution, we're going to have normality. And look at this is having a perfect shape of normal compared to when we did not do normal distribution. I'm going to show you. When we did not do normal distribution, look at something here. This is not that good. Okay, this is not that good. But with the sampling distribution that we have done, everything is actually going to work, the way we want it. Look at that. You see that now? Is there anyone who have any question before I go today? Is there anyone? Is there anyone who want to ask question before I go today?
Professor,
Okay, go ahead.
on this slide, when we're calculating the t-square statistic, so what do we plug in for di bar prime or di bar?
Oh, for what you're going to plug in for di bar?
Yes.
Yeah, what you're going to plug in for di bar, if you take a look at what I have here, okay, if you take a look at what I have here, what we actually want to get, what with this entity here, the 100,000 mean vector that I talk about is going to be like D1 here is just going to be 1 out of the 100,000. Do you understand now? 1 out of the 100,000. So if I put if I equal to 1, if I equal to 1, then I mean the first time, the first vector, one of the vector. Okay, so this is going to be the mean vector of one of that. So here it means one at a time you will be able to test for the for particular simulation. Okay, that was why you saw I right here. So that is what you're going to substitute. So the di bar here is actually going to be 1 of the 100,000. Does that make sense to you now?
Yes. So are they going to be given?
Yeah, it's going to be given. Yeah, it's actually going to be given. Yeah.
Okay.
Yeah.
Thank you.
You're welcome. Yeah. Is there anyone who want to ask question again?
Question. So why don't we use the chi-square QQ plus to test the bivariate normality in these slides? Because I saw that in the textbook, they use the chi-square plot. But in today's lecture, we only use 2 separate univariate normality tests. So
you mean normality test? Where do we do normality test? Can you tell me the slide?
why don't we use the chi-square plot for the bivariate normality test?
You mean why don't we use a chi-square plot for bivariate normality test? Is that what you are telling me?
Yes.
Oh, you are right. Today I think I'm going to show you. You were talking about this, right? Like that what we're using here is more or less like a univariate test of normality. Is that what you're saying?
Yes.
Now, why can't we use the bivariate? Of course, we can also use the bivariate. Of course, the right thing to use, it should be bivariate. Okay? Because I remember I told you before that if I got 2 variables, if on their own they are normally distributed, that doesn't mean they're going to be jointly normally distributed. You are right. So we have the assumption that even using that is still going to be normally distributed. Does that make sense to you now?
Okay.
Yeah. So we that is exactly what you said is what we're also going to use. But we have that assumption that okay, it's actually, and you know what? Even if it is not normal, okay, if I have, because let me let me tell you this. The reason why researchers nowadays why we normally take it when we conduct our research, and at the end of the day recommendation from the research don't normally see the light of the day, is simply because if you imagine if you are working on the 2 variables and you don't really no, you don't bother to test whether they are normally distributed or not. Because when they are normally distributed, the approach that we're actually going to use in statistics will be different from when they are not normally distributed. Because when they are not normally distributed, of course, we actually need to use the idea of sampling distribution, because when you do sampling distribution and going by central limit theorem, when a population that is not normal is actually going to be normal. Okay? So, and that is the reason why we care to know, we need to test. We shouldn't just assume, we need to test. Okay? Is there anyone who have a question for me before I go? Is there anyone? Is there anyone? Okay, I want to thank everyone, for attending my lecture today. Tomorrow, tomorrow is going to be a combination of a lab session and theoretical, because tomorrow we're going to move to multivariate test of means. Okay, let me just prepare your mind about what you're going to do tomorrow. Tomorrow, we're actually going to have multivariate version of analysis of variance test. Okay, tomorrow we're going to have, in analysis of variance, you normally test if there's an equality among groups, right? Okay, but when you are considering, you are only looking at one variable at a time, right, to do that. But tomorrow, I'm actually going to walk you through how can we test the equality of several means, equality of several means of variable across so many groups, okay? So what we have been doing before, we've been trying to look at multivariate test of mean in one population. We've done multivariate test of mean in two populations. And what we want to do tomorrow is actually going to be multivariate test of means in more than two populations, which is actually going to be a multivariate version of the analysis of variance. Okay? So please, I attached a material yesterday where I gave two sets of observation. Where I gave the one has to do with the bankruptcy, the other one has to do with the non-bankruptcy, and where you have several variables in bankruptcy, you have several variables in non-bankruptcy. That is a test of equality of means in two populations when you have several variables. Okay, and so please follow that that material very well, because I can actually give you a question to work on. Okay, now what we want to do tomorrow now is actually going to be if I have more than two groups. Okay, now let me pretend to you this way. Let me use different kind of diseases. We have a COVID-19, we have SARS, we have MERS. Now, let's say since I have SARS, MERS, and then the other disease, COVID-19, I got three variables. Okay, now these three variables, if we now select three groups, okay, if we now select three groups, maybe the three groups is going to be by country, okay, maybe United States, China, and Brazil, okay, or some, maybe three countries. Now in these three countries, we actually going to have we're going to collect three variables that I just mentioned. Okay, we can actually want to compare, the mean vector across the countries. Okay, the mean vector of COVID-19 cases, the mean vector of the other one, and so on like that. Okay, so will you do this a lot in economic analysis in spot analysis, in biostatistics, and so on like that. Okay, so I want to tell you that tomorrow topic is very, very crucial, and that particular material has already been uploaded. I want you to go through that material before we meet tomorrow. Okay, so I want to thank everyone for attending my lecture today. Make sure you stay safe, and if there is any one of you who need more clarification, of course, I'm also going to be having my office hour tomorrow. Okay, you can actually meet with me. Okay, and we can talk about it. Okay, so make sure you stay safe and have a good day.
Thank you.
You're welcome.